That's the same as having the squared here. Is that right? So the 2 has to come out, and then it's this to the first power. That's the first part, right, that I have? Now what do I need? I took care of the squared. What now? Derivative of secant of 2x. What's derivative of secant of something? What's derivative of secant? The derivative of secant x is secant x tangent x. Now, do we have x? We have 2x. So next to this is going to be times secant 2x tangent 2x. And then what? Times 2. Very good. So you got the 2 came out, secant 2x. Now the derivative of secant of 2x is secant of 2x tangent 2x. And then the derivative of 2x is 2. So we still have a 2 here. And what else do we have here? Remember, you're in the middle of a product rule, aren't you? You're in the middle of a product rule. So you got the first one next to all that. So times what? Negative 2x. This looks horrible, right? But let's not panic yet. Okay, derivative of the bottom. What's the derivative of tangent of 2x? Secant squared 2x times secant squared 2x times 2. Right? That's the derivative of the bottom? Yes? Did I? Oh, I forgot to put the squared. Thank you for catching that. That squared goes there. I don't know why I put that. Yes, thank you. That was this, right? Okay. Remember, secant of 2x is the same as 1 over cosine of 2x. So if I plug in 0 for x, secant of 0 is the same as 1 over cosine of 0, and cosine of 0 is 1, right? Okay, let's do this. What happens here? What do we get here? 0? What's that when we plug in 0? 1? Here? 1? Well, okay. Let me do it this way. Negative 4 times 0 times 1 plus 2 times 1 times 1 times, wait, what's this? Tangent of 0, 0 times 2 times negative 2 times 0. Do y'all see that's the top? Okay. It looks bad because isn't this all 0 on top? That's 0, but is the bottom 0? It's not 0. The bottom, this right here, is 1 squared. That's 1 times 2. And so you get 0 over 2, and that is just 0. You don't have 0 over 0 anymore. And so we have the natural log of y equals 0, and now you do e on both sides, and you get y is 1. So the answer is 1. Questions? All right, can we move on? Make sure you do your homework for this section because, you know, this problem, there's a lot going on here, right? You got to keep track of a lot of stuff here. So, but do you agree that this was doable compared to the one we had last time? I mean, like, it got ugly, right? As long as you did your derivatives right, it got there though, right? It wasn't like just continually getting worse and worse. And our derivative wasn't that bad. I'd say we had to do one pretty bad derivative, but that was about it. All right, we're moving on. Chapter 4. Chapter 4. Good question. I thought it was like in November, right before Thanksgiving. Now, we might change that. I don't know. That's going to be a pretty big test.
Especially before Thanksgiving?
Yeah, I know.
But then
What we might do is have it the week before.
Ooh, I'm sorry, that's my fault.
Well, to not have this on there, to not have 4.5 on there.
The week before is perfect.
Yeah. Now that, I mean, like historically I've done that a lot, where I've moved it. It's just that 4.5 is a natural place to say we're done with this material. I mean, sorry, yeah, 4.5 is a good place to say, okay, all that stuff goes together, right? Now, if we make the test a little, sooner, then after we finish that test, we're going to be continuing that same sort of material, and then we're going to transition into something new, which is fine. But yes.
100% it's going to be the 15th.
What do y'all think? 15th? Would y'all rather have a test? What would that test have? It would have related rates, word problems, right? Spheres growing. It would have implicit. Did y'all have implicit on the last test? I don't remember the last. Let me see. Yeah. Let me look at it. The last question. Yeah, we stopped at chain, right? Yeah, our last test stopped at chain rule. Which means you what?
I said I was missing the previous material.
Oh yeah.
Looking at it now, I'm like,
In Cal 2, you'll wish you were back in Cal 1.
from this chapter,
So we have a lot on this test. We have 2.6, 2.7. Chapter 3, 3.3 is exponential and log derivatives, right? 3.5 inverse trig derivatives, and then L'Hopital. I mean, that already is a lot, and we're still got to get through 4.1, 4.2, 4.3. We could probably push 4.4 and 4.5 to the next test.
I was going to say, does that mean that we're going to have, will we have a quiz on the 22nd?
A quiz?
Yeah, because we're going to move material down and then move the test.
What do you mean a quiz on?
because the quizzes aren't like planned.
Yeah, the quizzes are just whenever.
Just give it to us.
Yeah. You're requesting a quiz on the 22nd.
I'm requesting it.
Okay, let me get that down on my
Well,
calendar.
If you request it, we don't do it any other day. 'Cause I can plan.
Now, let's try and plan for this. If we do 4.1 today, 4.2 next week, 4.3, would y'all rather do it on the 15th, which would be a Tuesday? Wait, no, how about the Thursday before? How about the 17th? Would y'all rather have it on the 15th or 17th?
17.
17th is a Thursday. Let's take a vote. 15th is Tuesday. 15th is a Tuesday. It's all right. I mean, vote.
Yeah, okay, 17th.
No, 15th is a Tuesday. 15th, right? Okay, 17th? Okay, let's do that. We'll say that officially we are going to move our test one day back to the 17th, all right?
Are you getting married?
Yeah.
Congratulations.
I'm not ruining anything, am I?
Well, that's why I don't want it on the 15th. I was like, I don't know.
Okay, so you don't want the 15th. The 17th works?
One thing no one else.
And that's what we're doing, right?
Yeah.
17th. All right, so November 17th, right, is going to be exam 3. All right? All right, well, let's get into chapter 4. Oops, sorry. So I have all these notes are online for you, okay? Chapter 4, whoa. Chapter,
You did spell L'Hopital, by the way, correctly.
I do what?
You did spell it correctly without the S.
Where?
In general, we were talking about that like 2 weeks ago, how you spelled it.
I thought I misspelt it in the calendar.
No, there is no S. Like the S is sometimes. Like, some people spell that.
No, where? The S in it's before the P.
Yeah, there is no, it's not. There's an accent on the O. It doesn't matter. I'm sorry. I shouldn't have brought it up. I apologize. But,
You're not saying at the end of the word, you're saying in the
I'm
word?
saying in the word. In the word where you added it in the word.
Yeah.
We were this whole conversation about it.
Yeah.
I looked it up and didn't spell it wrong.
Really?
So sorry. That's my fault. I really did not mean
In the textbook, it has an S.
I believe you.
Yeah. Okay. All right. All right, so applications of differentiation is the title of this section, chapter. And there's a lot here, okay? There's a lot here. The first part of this, 4.1, is very visual, so I think it's going to be easy for you to understand what we're trying to accomplish. It's just the actual doing it is, where things get a little messy sometimes. So I think what I want to do here is just give you this real quick rundown of the main two ideas of this chapter, all right? All right, so we'll say, this is idea 1 and idea 2. These are the main two concepts, all right? The first idea that we have here is this. If you have a function that starts at some point and ends at some point, okay? So what we would say here is that you have a function that is defined on a closed interval. Okay, so this function, f of x, is defined on some interval a comma b with brackets on the ends here, which means that if you plug a into this function, you get a point. If you plug in b, you get a point. And if you plug in any number in between a and b, you get points, and you get this nice function, right? If we have a function that is defined on this closed interval, for a function that is defined on a closed interval, can you tell me what the highest point on that function is, and can you tell me what the lowest point on that function is? I mean, it should be there, right? There should be a highest and lowest point on this function somewhere. Can we find it? That's the first idea. So here, do y'all see the highest? Well, my graph kind of sucks. Because the highest point's where? At the right end point, right? And the lowest point's where? Right there. But if I drew it a little different, right? What if I drew a graph that did something like this? Let me do another one right here. What if I did this? Starts here, went up. What if I did that? Then the highest point is somewhere else, right? It's inside the interval somewhere. That's our highest point. That's our lowest point. So there's all these different cases we could have. It could be at the ends or in between somewhere. But the first idea is that if you give me a function on a closed interval, I should be able to find the highest and lowest points, right? And that's what 4.1 is about. 4.1 is about finding what we call the maximum and minimum values of the function. The second idea is, what if you have a function that is not defined on a closed interval? So what if the function is not between a and b? What if the function does something like this? Like a polynomial function. Does this function have a highest point? Yes. You can see it, right? Does it have a lowest point? No. Right? So here we have a function f, right? F of x, we'll say, is defined on, in this case, it looks like it's defined everywhere, right? From negative infinity to infinity. This is called an open interval. And the question would be, can we find the highest and lowest points of this? This is called, we will refer to this, finding the highest and lowest points here, we'll call that the closed interval method. And over here, we will call this the open interval method. There are two different techniques to do. To do this, there's one technique. And to do this, it's a different technique. The technique to do this is harder than the technique to do this, all right? So when we're in this section, one of the first things we're going to ask ourselves as we move through the section when we get to these harder problems, 4.5 are the word problems. That's the section everyone hates, all right? When we get to that, the first thing we're going to ask is, which of these two cases are we in? Are we here or are we here? And then once we determine that, then from there we proceed, all right? So today we are going to look at the first concept, this first idea of the closed interval method. So let's go back to Oh shit, I just pressed the wrong button. How y'all doing? I just totally messed up this system. No, I'm gonna have to wait for this to come on so I don't know what's gonna happen here because they're out of sync now. So what I need to do is I need to turn this off. But I have to wait till that blue light stops flashing. There it is. This is why IT doesn't want me doing this, because they don't want me getting things out of sync. And I may have just done that. Come on. There we go. Okay. What I meant to do was turn off the lights. Let me see if I can turn this off. Should I just leave this up for now? Let me just leave this up so we can look at it up here for now. Because a lot of this first stuff is very visual. Okay, 4.1, maximum minimum values. And there's a bunch of notes in here. So the first note is, what is the definition of what we call the absolute maximum and minimum values of a function? So here's the definition. Don't go trying to write this all down. That's not the point. I'm just going to read through it for you. Given a curve f defined on some domain D. So give me some function, right? And give me its domain. Some number c inside that domain. So if you look at this picture here, like some number in here c, right? Somewhere on here c is called the absolute maximum value of the function on that domain if f of c is greater than or equal to f of x for all x in the domain. All that means is that when you plug c into the function, your output, f of c, is bigger than every other point on the graph. So it's the highest point. That would be your absolute maximum. Does that make sense? The absolute minimum is the reverse. It's some number c that when you plug it in, it is smaller than or equal to all the other points on the graph. So that would be your minimum value. In either case, f of c, remember f of c is the y value, right? So the height of the point. That value is called the global maximum or global minimum of the function. So if you're looking at it, if you're looking at the absolute maximum, you could also call that the global maximum. If you're looking at the absolute minimum, you could also call it the global minimum. Make sense? All right, the next definition we have is what's called a local maximum. And this one's a little tricky. Given a curve f defined on some domain D and some number c in the domain, f of c will be called a local maximum value of f if f of c is bigger than or equal to f of x. This is the big difference right here. For all x near c. So the previous definition said that that point had to be the highest point out of all the points on the graph, right? This says you just have to be the highest point locally. What does that mean, near? Remember us having that conversation about, are we close to each other? Are we close to SeaWorld? Are we close to the sun, right? Like it's a relative term. So we have to kind of wave our hands at that a little bit in this class, like what does near mean? But when you see the pictures, I think it'll make sense, right? So this just has to be the highest point locally, which is why we call it the local maximum. And then if the point is the lowest locally, we call it the local minimum. All right? If your function is defined on a closed interval, so if you're back in this scenario over here, the two endpoints are always considered local maximums or local minimums. So you see this point here? That would be considered a local minimum because it is low. It's the lowest point relative to the points near it. And this would be a local maximum because it is the highest point relative to the points that are near it. Understand? I'm going to show you, now it's just going to be pictures. Let me show you some pictures and then we'll kind of talk about what things are. So visualization, take a look at this graph, maybe. It's not what I want. Still not what I want. That should be okay, right? You can see that? All right, this function is defined on a closed interval. Do y'all see that? Starts at a point, ends at a point. Let's talk about global. Well, let's talk about, man, it's hard to see with this graph. It's hard to see, maybe from where you're sitting it'll be easier. I don't know, it's hard when I'm up close to tell. Can you all see, does this graph have a global minimum? Does it have an absolute minimum value? Where is it? Somewhere over here, right? Right in here? That's it, that's your global minimum. That is the lowest point on the graph out of all the points, right? That's your global minimum. How about a global maximum? It's hard to tell. These almost look like they're the same height, but I think this one's a little higher. Right? That's the highest point on the graph. So that graph has a global minimum and a global maximum. The global maximum is the actual value. It's how high this point is. It would be the y coordinate there. That's your global maximum. Your global minimum would be your y value right here. All right? How about local? Let me plot the globals here. Here's your globals right there. So here you have a global maximum. It happens at 2, and the value of it is 856. You have a global minimum. It happens at -5, and the actual value is -4,975. Okay? Local. Let's think about locals now. I like to think about locals like King of the Hill, right? You can have you ever, no? Did you ever play that game? No? Get a mound of dirt and see who could stay on top, push everyone else off. No? King of the Hill. Well, locals are like King of the Hill of that hill. There's multiple hills, so you might have other kings of other hills. And also you could say the valleys also are like King of the Valley, right? If that's even a thing. All right, so let's start with the endpoints. The 2 endpoints have to be locals, all right? So this is a local what? Is that a lowest point or a highest point relative to it? So if you were to just kind of focus just here, if you're looking just in here, that would be the highest point over there, right? So that would be a local maximum. What about this one? Same thing, local max. If you kind of just ignore all that, then this right here would be the highest point in that little neighborhood, right? When I say neighborhood, that's a mathematical term, so I'm not just using a weird name. We say neighborhoods when we talk about math. Okay, so that's a local max, that's a local max. Let me take these points off of here. How about the global minimum? Would the global minimum also be a local minimum? Yes. Yeah, because it's the lowest point in this little region, right? So that's a local minimum. That would be a local maximum, and that would be a local minimum. Now, when I did this, I forgot to put the 2 endpoints. So the 2 endpoints are also local maxes, but I have a local minimum here, local max, local min. Yes?
Is that, so every time it changes direction, from up or down, is that a new local?
Every time it changes direction from up to down,
Yeah, up to down, back and forth. It doesn't matter how close or how high the frequency is, it just matters.
I think that's a good question for you to ponder. What do you think? Can you think of any case where that wouldn't happen? You're saying if it goes up and then down, we should have up there a local max or something, right?
Yeah,
if it goes up and down.
Locals throughout the whole thing, but it doesn't matter how high the frequency is. So how people squish it.
Oh yeah, no, that doesn't matter.
It doesn't matter at all, right? How close that is.
No. But you have to be careful because what you just said is if it goes up and down, then that has to be a local max, right? That's what you said? Like if it goes up then down, then you should have a local max there?
Yeah, if you have a hill and another hill,
Yes.
it doesn't matter how close the hills are together.
Let me challenge you with this idea. Let's say we have some point here, let's just call it C. And what I tell you is that to the left of C, your graph goes up. And to the right of C, your graph goes down. Is that enough for you to tell me that at C you have a local max?
No.
What do y'all think? I'm seeing no's, I'm seeing yeses.
Could be a last node
It could be an asymptote, right? What if right here it did this? And then right here it did this. Then do you agree that to the left of C you're going up?
I thought it had to be
I
fine.
know, I thought we're talking about.
This is a function.
But like a closed.
Ah, there you go. That's what I want to hear. So when we get to this theorem in a minute, it's going to require continuity. Okay? You need the continuity because if you don't have continuity, you could have things like this happen, and then when you say that, I can't guarantee that it's a local max. Now, if you force it to be continuous, then I will agree with you. So good, you're already making a point that I'm going to make in a little while, so that's good. Does everyone understand? The statement was if the graph goes up and down, then we should have a local max. This goes up and then down, it's not a local max. Add the condition of continuity, then it has to happen because this is not continuous, so you can't consider something like this. All right, good. Can I continue? How about this one? This is not a trick question, okay? Do y'all see the global maximum? Where's the global max? Far right endpoint, right? Global minimum? Right here? Bless you, bless you. There's your globals, right? And then your locals are going to be endpoints, local max, local min, local max, local min, local max. Yes?
Is that far left point a local map?
Local max. When I did this, my label, I didn't label them. It's my mistake. I'm pointing it out though. All right, so for this one, these are arrows, okay, that go forever. So do we have a global minimum? Yes, right there, global minimum. That's also called the absolute minimum. And there's another word for it. You can call it an extreme minimum. That's why I have here, see, extreme values, right? So I either have a global extreme or a local extreme. So this would be, we have one global minimum here. Do we have a global maximum? Do we have a highest value of this function? No. And infinity is not an answer. Okay, it would have to be a number. So infinity is not a number, so it has no global maximum. So I will put that here. I have no global maximum. I have a global minimum though. Yes?
I had a question about the endpoints.
Yes.
If we assume that the line is continuous and both or whatever endpoint we're talking about is closed, can we assume that those are local maximums and minimums?
Wait a minute. You're saying if we have a closed interval, right? Two endpoints,
And the endpoints are closed endpoints, like they're not
Yeah.
open. Yeah.
then those have to be local somethings, either local max or min? Yes. I think I said that, no? It's in the notes. No, if I didn't stress it enough, I want you to know it's right here. If a function is defined on a closed interval AB, then the endpoints are always considered to be either local max or min. Okay, how about this? Those are my globals, right? Global min, global max, local min, local max, local min. I have one more. This is an example to show you that our global max, right? Our global max occurs at two different points, right? At this endpoint and this point, the global max is how high those points are, right? So here our global maximum value is just how high that is, right? But it happens at two places. It's there's another example I could give you. If I take a sine function, that might be an easier one. If I take the sine function and just do a couple of periods of sine, there we go, right? Let me just start here and end here. What's the global max of that? 1. Now, it occurs here in this picture at three different places. But the global max is the value it achieves. How high does it go? The y value, right?
It wouldn't matter, right? Because it's still the same. Why not?
That's right. So your global max is 1. The global maximum of this is 1. It occurs at three different places. But the value of the function is the global max. What's the global minimum? -1, and it would occur here and here, right? 2 different places. But the global minimum is -1. And then you'd have local max, local min, local max, local min, local max, right? All right, let's go. Our first theorem, the extreme value theorem. I'm going to make this bigger so you can see it. All right, so this is what we were just talking about. I'll make it a little bigger. Bigger. If f is continuous, right? If f is continuous, which means we can draw it without picking up our pencil on some closed interval AB, then f attains both an absolute maximum and minimum value on the interval. So, I mean, I think this is pretty intuitive. If you tell me that I have to draw you a function, right, that starts at some point A and ends at some point B, and that it's defined on that closed interval and that it's continuous, so I can't pick up my pencil, no matter how I do this, I'm going to have a highest and lowest point. I'm going to have to, right? It doesn't matter what I do, right? However I draw it, someone's going to be able to go tell me what the highest and lowest points are, right? Yes?
What if it's a straight line?
Ah, good. What if it's a straight line? You mean horizontal, right? Because a vertical line wouldn't be a function.
Right.
Okay. Let's just say that this is 5 here. What is the absolute maximum value?
5.
Good. What's the absolute minimum value? 5.